Today's going to be 10-4. We're going to be graphing linear equations and looking at the average rate of change. So today's objective, we're going to graph linear equations and find the average rate of change of a function. So our first example here, it says graph the given function. Now, even though it's eventually going to simplify into a linear function, we have to examine the domain still. So if I were to factor the top, it would factor into this x plus 2 and x minus 2. Now these x minus 2's cancel out, and so I'm left with x plus 2. Now even though I can graph this x plus 2, it would be almost like an omission of sin of omission if I were to ignore this x minus 2 that canceled out, because it is part of this function. So even though I may use the x plus 2 as part of my graphing, that x minus 2 that I canceled out is still part of my function. And so if x can't be 2, right, because if I plug in 2 here, 2 minus 2 is 0, 2 minus 2 is 0, I get 0 over 0, which is that indeterminate case, I have to be careful about what this is going to imply. So using this function x plus 2, if I were to graph it, notice I picked values, -1 plugged in, 0 plugged in, 1 plugged in. If I plug in values, so let's take a look at my graph. I have this little open circle here at 2. Now that's my undefined value, and that's the way that we would represent this type of undefined value. Now, this type of undefined value is called a point of discontinuity, and what we would do to be able to find where do I place it, well, I'd look at the simplified version, which is 2. So if I plugged in 2, I get 2 plus 2, so that's going to be 4. And so at 2, 4, that's where I'm going to put my open circle. And so we're not really going to go into depth on this, but I just kind of wanted to briefly introduce, just to understand that we can't ignore these undefined values when they exist. So we have to pay attention to my domain. And just remember, we're going to keep cycling back over and over and over again to that domain. And so to graph it, just remember, we just pick points at -1, 1. So at -1, 1, that would be a point at 0, 2, at 1, 3, 2, 4, that's the undefined value, so I put an open circle. At 3, it's 5, etc., etc. Now example number 2, if I wanted to graph this, we just create our chart. And so if I plug in, let's say, these values here, if I plug in -1, -3 minus 1 is -4. If I plug in 0, I get -1. If I plug in 1, I get 2. So then plotting these on my graph, at -1, it's -4. At 0, it's -1. And at 1, it's +2. And so that's going to be the graph of my equation. Now, one thing that we saw in common with everything we've done so far, examining these lines, is the slope is constant throughout the entire line. If I pick these 2 points, or these 2 points, or these 2 points, I can pick a series of points here, and my slope's always going to be the same. Now, what if I wanted to find the slope between 2 points on a graph that's not a line? Now, if I want to find the slope of a graph that's not a line, we call this the average rate of change. So defining the average rate of change, we're going to say let f be a function defined on the interval AB. The average rate of change of f over that interval AB is defined as the change of f over change of x equals f of b minus f of a over b minus a. So this equation here is the equation that we're going to use when we're trying to find that average rate of change. Now geometrically, if we have the graph y equals f of x, the average rate of change on that interval is the slope which connects these values. Now just to interpret it, a and b are just x values. This f of a and this f of b, those are the y values that I get after I plug a and b in. And so we call this line that's created, so this line that we get here, we call this line the secant line. Now, as opposed to once we get to calculus, we're going to take this point here, and we're going to take this point and we're going to move it closer and closer and closer and closer to the first point that we picked. And as we move that point closer, eventually it lands right on top of each other, and that's going to create our instantaneous slope, and we call that instantaneous rate of change the tangent line. But we're not worried about that yet. We're not going to really focus on that at all. Right now we just need to focus on the secant line and how to calculate it. Now to help us visualize this, we're going to use this analogy. Let's say we traveled 100 miles in 2 hours. Now my average speed is going to be this 100 miles over 2, which gives me 50 miles per hour. But that doesn't necessarily mean that I drove 50 miles per hour the entire time. You know, there could have been traffic in the beginning and I was driving slower, and then it sped up towards the end and I was able to go faster. And so all this is the average over that given interval of 2 hours. From time equals 0 to time equals 2, this is going to be the average that it gives me. Now what your speedometer reads is the instantaneous rate of change. And that's that central theme of calculus that I pointed out in the previous slide. So for this first example, let's compute the average rate of change for this function over the interval. So for this right here, this is going to be, we said it's delta f over delta x, which is going to be the change in my function over the change in my x's. So I'm going to say b minus a. So that means my f of b is going to be 1 cubed minus negative 1 cubed all over 1 minus negative 1. And so plugging that in, I'm going to get 1 plus 1 over 1 plus 1, which is 2 over 2, which is 1. And so my average rate of change is just going to be the slope of 1. For this next one here, plugging it in, we said f of b minus f of a over b minus a. So plugging that in, plugging in 2 minus plugging in negative 2 over 2 minus negative 2. So I'm going to get 8 plus 8 over, and then adding these together I get 4. So 16 over 4, which is going to give me 4. And so that's going to be my answer there. And I'll do one more. So that's plugging in 3. So we get 3 cubed minus negative 3 cubed over 3 minus negative 3. So that gives me 27 plus 27 all over 6. So that's 54 over 6, which is 9. And so that's how we compute the average rate of change. You just plug it into the definition. And if you notice, it is very similar to y2 minus y1 over x2 minus x1. It's basically identical. We're just defining the definition just slightly different. So now let's look at a word problem. It says, recall that the revenue from selling X units at price P unit is given by the formula R equals X times my price demand function. So if my price demand function for Portaboys is determined as P of X equals negative 1.5x plus 250, find and simplify the expression for the weekly revenue R of X as a function of weekly sales X. So I'm going to use this equation here, R equals X times P. So my revenue equals X times my profit function, sorry, my price demand function. So I plug that in, so I get X times 1.5x plus 250, distribute, so if I take that X and distribute that through, and then from there, I need to write it as a function notation, and so this is going to be my profit function, or my revenue function. Number 2, it says find and interpret the average rate of change of R of X over the interval 0, 50. So this is my A and this is my B. So it's just going to be the change in R over the change in X. So my revenue with 50 plugged in minus my revenue with 0 plugged in over 50 minus 0. And so if I go through and simplify, now use a calculator for this, make it easier on yourself. And I'm going to get 150. So I can say for every Portaboy sold, revenue increases by 150 bucks. And then the third, it says find and interpret the average rate of change of R of X as it's from 50 to 100. So this is now going to be my A, and this is going to be my B. So my interval is going to be 50, 100. And so now plugging those in, R of 100 minus R of 50 over 100 minus 50. Enter all that in your calculator, simplify, and you get 25. Now, so for every additional Portaboy sold within that range, now it's going to be an increase of $25. So it's actually less. So that means to increase the demand, I really had to lower the price. So this is find and interpret the average rate of change of the weekly revenue as weekly sales increase from 100 to 150. So now my interval is 100 to 150. So now entering all that in there and simplifying, I get negative 125. And so that means that we're losing $125 of weekly revenue for each additional Portaboy sold. Now, one of the reasons why this would be possible is we have to really, really reduce the price to increase the demand that we want. And so we're basically losing money to get people to purchase the product. And so that could be one of the explainable reasons. The last thing I want to talk about is re-examining the difference quotient. Now, all the difference quotient is taking our function f over the interval x comma x plus h. So this would be my a, this would be my b. Now, if you don't, like if this is kind of like weird to examine, let's just think of x squared. What if I say my interval is a over my a interval ab? We said that that was going to be x and x plus h. So that means that if I were to do f of b minus my f of a, so that should be x, over b minus a. Well, those cancel out, and so that's why I'm left with my f of x plus h minus f of x all over h. And so that's all this is. The difference quotient is just going to be, it's just finding the average rate of change over a different interval, and the interval we say is x and x plus h. So this sums up our lesson. If you have any other questions, please leave them in the comments.